Here in the UK, we import 100% of the lithium, nickel and cobalt needed for batteries. And that seems daft to me, not least because it makes the UK pretty vulnerable in the critical raw materials department. But it needn't be that way, because during a battery's life, those critical raw materials don't really get used up. So come retirement, the nickel, the lithium, the cobalt, it's all largely just sitting there ready to be reused. So if you could recycle those EV batteries, turn those batteries back into their constituent components like this, then that is a real win, not least from a sustainability point of view, so that we're not digging virgin raw material out of the ground, but also to create a homegrown supply chain of those critical raw materials. At least that is what Altilium hopes, and we've come to their pilot line facility here in Plymouth to find out a little more. Welcome to Everything Electric Tech. Our 3 free YouTube channels on EVs and clean energy tech are funded by our fun-packed Test Drive-tastic events in the North, West and Greater London, and our events down under. Next up, Everything Electric North 2026. Plus, check out everythingelectric.store for merch and much more. Back to the episode. So here at Altilium, the team have been busy squirreling away, turning old battery packs into black mass into its eventual constituent components. And it turns out they're pretty good at it. In fact, they can recover over 95% of cathode active materials, 97% of lithium and LFP batteries, and over 99% of graphite. So the black mass comes here to Altilium. But where do the EVs that make the black mass actually come from? What's the source presently?
Yeah, so I think one of the uniquenesses of what we're building at Altilium is that we're in the UK. The UK is an island. It has really high adoption of EV. We have over 1.8 million vehicles on the road. Also, we have gigafactories operating and being built, and all of that scrap needs recycling and putting back into the supply chain. So Altilium's ACT-free project will process 24,000 EV batteries per year, and that will start in 2027. So we're confident that there's enough scrap here in the UK because we have the first generation electric vehicles coming to end of life, for example, Nissan Leaf, and also we have a number of vehicles which have been involved in car accidents, and we have a good stock of batteries which are in scrap yards which can be put into Altilium's refineries, and we can recover those materials and put them back into a UK supply chain.
So at the end of this process, what do we end up with, and where does that eventually go to as well?
Well, the black mass we started with has a lot of components, but what we really want to do is extract those cathode active material components. So that's the nickel, the cobalt and manganese, and the lithium, and then use that to rebuild a fresh consignment of cathode active material. There are a number of other materials that come out along the way. So there's graphite, there's copper, to name a few.
So we start with our black mass. This is shredded battery materials. And the very first step is to add sulfuric acid, or H2SO4, if you remember your GCSE chemistry. That dissolves all of the metals, which means that it becomes much easier to filter out our graphite. Then the next steps are all about removing the other impurities that exist within the batteries. I say impurities, they're just not necessarily used for cathode active materials. So we have gypsum, which could be used in the building industry, and of course a little bit of copper. To give you an idea of how much copper, let's imagine that we had 100 kilos of black mass. We would end up with about 2 to 3 kilos of copper. Now, this is the exciting bit. This is how we get our cathode active materials. So now we have removed the graphite, we've removed our impurities, and we want to separate out our nickel, our manganese and cobalt. So this is done through a combination of solvent extraction and precipitation, but we start with our solvent extraction. So here we have a solution which would contain some of our manganese, and we also add a layer of kerosene which has an extractant agent added within it. Now, kerosene is an oil and it doesn't mix with water, which is why we have these 2 separate layers here. So these can be mixed together very, very rigorously, and then we can dissolve the manganese in that kerosene. That will produce this, which will also have some impurities in, so that needs to be scrubbed in order to create this, which then can be dissolved back into the solution. So here is our manganese solution, but it could be dried to make this, our manganese sulfate. So now what are we left with? Well, we have our cobalt And we have our nickel and we have our lithium. So we have a very similar process again to separate out to our cobalt. That's all about using solvent extraction. And now finally we're left with our lithium and our nickel in that solution. And actually nickel and lithium are reasonably easy to separate from each other. So we can use a precipitation process instead. So think of it like a kind of lime scale being left in the bottom of your kettle. That kind of solid can be produced from that solution. And that's how we end up with our nickel sulfate. Lastly, we have our lithium, which at the moment is a lithium sulfate, and it needs to be turned into a lithium carbonate in order to be used in that cathode active material. So these materials, these solutions, which are our nickel, our manganese and our cobalt, they're sent next door to make our precursor cathode active material. And our lithium carbonate are mixed in some sort of chemistry magic in order to make this, our cathode active material, specifically NMC 811, to make next generation battery cells. When we look at that black mass, it is so dense and filled with things that are valuable in a way that no ore that we dig out of the ground would have that same kind of concentration in the same mass. So is this really that much less environmentally intense than digging things out of the ground? Like, how good is it really?
Let's draw a comparison. NMC 111 material, if I take a consignment of that as black mass, it'll be about 12% nickel, about 12% cobalt, about 12% manganese, maybe 3-4% lithium, and about 30% graphite. That's our headliners. But if I want to go out into the world market and find a ton of nickel, I'd have to look at the most productive nickel mines in the world, which are probably in Indonesia, and their ores run at about 2% yield. Okay, so if I want my 1 ton, I need to go and dig 50 tons of rock. We then need to process that 50 tons of rock, and we need to find somewhere, some hole in the ground for the remaining 49 tons that I don't want to go and sit. If I want to do the same with cobalt and I want my 1 ton of cobalt, I probably have to go to the Democratic Republic of Congo, where the corallite mines down there run maybe at 0.5%, so even lower yielding. So for my 1 ton of cobalt, I'm going to need to dig 200 tons of rock. Process that 200 tons of rock, find a hole big enough to take 199 tons of waste, and there's my 1 ton of cobalt. If we look at the black mass itself, if I want 1 ton of nickel from that NMC 111 black mass, I only need 8 tons of black mass. And that same 8 tons of black mass is going to give me, as well as the nickel, it's going to give me that cobalt. And it's going to give me the same of manganese. And it's going to give me just shy of half a ton of lithium as well, and about 3 tons of graphite. The entitlement of black mass is a massive, massive part of the environmental credentials of this process. And the alternative to digging up fresh out of the ground when it's already available in society for us to take at the end of any EV's life, can't ignore it.
So when we compare the amount that's in black mass versus the amount that's in the ground, it is evidently just a complete no-brainer. And we know that this is definitely less energy intense than that digging out of the ground. But this is still an industrial process. So what are the sources or the most energy intensive parts of this particular process?
The process we've developed, the extensive hydrometallurgical flow sheet we've developed, first of all, doesn't contain any roasting or furnace operations before we start making the CAM at the end, which is a big benefit to the total energy usage. Secondly, we've made very deliberate choices in the feedstock chemicals that we use, those that already have established very energy and resource efficient supply chains throughout the world and are able to meet the volumes that we demand. Okay, so if this is a several tens of thousands of tons problem for being able to recycle black mass, we're going to need several thousands of tons of, for example, sulfuric acid. Sulfuric acid is available in that volume. Things like deep eutectic solvents are not available in that volume. And so at the moment, the industry of chemical supply can't answer that problem. Further, we've managed to balance all of our processes so that all of them actually are undertaken at a relatively benign temperature. There's no superheating. There's very few direct swings from hot to cold or anything like that. So it's actually just adding a chemical, giving it some time in a tank, separating our waste from our target material, and moving on to the next stage.
The UK has just launched its critical mineral strategy, Vision 2035, which is a roadmap that lays out how the UK is going to secure its critical raw materials to supply the things that we need for everyday life. So not just electric vehicles, but also wind turbines, solar farms, defence, healthcare, you name it. And there's a real urgency to this because by 2035, it's anticipated that lithium demand is going to increase by 1,100% here in the UK. Copper demand is going to double. And throw into the mix that currently supply chains are extremely concentrated in certain countries, ergo China, and those supply chains are becoming more and more geopolitically exposed. So this isn't just an industrial imperative, but a super strategic one too. So what's the plan? Well, the UK hopes to secure 10% of industrial demand through extraction, refining and processing right here in the UK. It hopes to meet 20% of demand via recycling, and it hopes to diversify imports such that no more than 60% of any single mineral comes from a single country.
Now add the Brexit factor, and this becomes even more important for car makers like Jaguar, Land Rover, Nissan and Mini. Now, under UK-EU trade rules, electric vehicles can only be exported tariff-free if a sufficient share of their value comes from the UK or EU, and those rules tighten sharply in 2027. A battery made in the UK using virgin materials from China may no longer qualify, triggering a 10% tariff. But here's the thing, recycled materials processed in the UK do count as UK origin. Then throw into the mix that from 2036, EU battery regulations will also mandate minimum recycled content for lithium, nickel and cobalt.
And that's why Altilium's timing is so timely, and it is no wonder that Jaguar Land Rover are putting their battery cells to the test.
Yes, we're very fortunate to have support from Innovate UK and the Advanced Propulsion Centre, and we have two projects. One is APC 23 with Nissan, and we have just completed one project called ARMD3 with JLR. So the work we've been doing is showing that recycled materials can perform the same as commercial materials. In the case of JLR, we built automotive grade multi-layer pouch cells from old I-Pace vehicles and production scrap, and those batteries were shown to be 32% lower carbon than today's batteries.
Walking around here and looking at all of the individual processes, they seem remarkably simple and straightforward, and actually processes that a lot of people will be familiar from their time with GCSE or A-level chemistry. But there must be some magic or some IP that makes this particularly unique. So where is the hard science? And I ask that in the least facetious way possible.
The hard science is kind of wrapped up in the challenge, right? The black mass is the challenge. We talked about it being an extremely rich feedstock. It's well worth going after everything that's inside there. But if it's rich in all these different things, that also means it's a busy chemical landscape to try and actually extract efficiently from. So yes, individual processes might look quite simple. You know, we have a certain leach solution, we apply a base, and we hit a threshold pH and temperature. Fantastic. But it's the sequencing of those processes, it's the fine-tuning of those absolute optimum conditions of those processes, which allow us to, first of all, have very, very high extraction rates on what we want, have very, very low loss rates on what we want, even as cycles go on, as the flow chain kind of, as you move down that flow sheet, our losses of our target products are very, very low, stage to stage. And it's really, really important for us to show that we can do this efficiently, and that actually that every component of the black mass is important enough to care about the efficiency of extraction.
The pilot line facility is capable of processing 100 tonnes of battery materials per year. So certainly not about huge volumes, but all about proving the process. Meanwhile, this plant, just 15 minutes up the road, will be capable of processing 8,000 tonnes per year, equivalent to 24 to 30,000 EVs worth of batteries.
And they're also exploring another facility in Teesside, an area that already has deep expertise in battery materials and synthetic graphite. And the facility there will have the capacity to recycle up to 150,000 EVs annually. And that could generate around 30,000 tonnes of cathode active material, enough to supply roughly 20% of the UK's expected demand by 2030. But all of this has got me thinking. Electric vehicles are lasting far longer than many originally expected, often 15 to 20 years. So does that mean that large-scale recycling is still a decade away? And if so, can recycled cathode material actually make a meaningful dent in car makers' production needs anytime soon?
As we move forward later this decade, basis the UK high EV adoption and it being an island and battery recycling is essentially a localized industry, we feel that there can be a real contribution of critical minerals coming from old EV batteries into a UK supply chain. So, ultimately we're looking at supporting UK industrial resilience and onshoring supply chains here. And what we believe is that by 2040, over 50% of the critical minerals needed for an EV battery supply chain can come from recycling.
If you look around you, everything, and I really do mean everything, is either grown or dug up out of the ground. It has to come from somewhere. And if we just throw it away, where even is away? There is so much embedded value in the materials that already exist in the world today. And if we can recycle them, we can retain that value. And more than that, in the case of battery materials, we can create a supply chain right here in the UK and the jobs that also go with it. As we've seen today, recycling battery materials is not only the sensible thing for the planet, but it's infinitely more strategic. But that is all that we have time for today. Please do let us know what you think in the comments. Please do like and subscribe. And if you have been, thank you for watching.